Yeah, hi everyone again. I am Merve. I am from Ericsson Research based in Sweden. And also I'm a PhD candidate district Leuven. Today I will present our work monitoring, mitigating initialized memory access with conditional capabilities. This work is jointly done with Ericsson Research, Leuven and University of BULB. Okay, let's get started from memory safety, my main research area on memory safety, and I am really happy to see that concern around memory safety in software industry are increasing getting attentions thanks to the regular attentions. Uh, especially regulator says that you should have a roadmap soon. uh, if I checked what is memory safety is a combination of correctness aspects which can be improved through a number of means. For example, even though there is no formal definitions, we can define as a spatial safety, temporal safety, or initialization safety. How we can achieve memory safety? We can achieve using memory safe programming language, Rust, but if you consider million of C and C++, of course, it will be so difficult to transitions to the Rust. And you can use on your products static or dynamic analysis. Static analysis have heuristics. Dynamic analysis has a performance bottleneck. That's why recent attention is memory safe hardware, CHERI. Why it is really important? Because of that is you can just get your C and C++ code and run on the CHERI hardware. Today, I will focusing on this CHERI hardware, and also I will focusing on the initialization safety. Why does initialization safety matter? A programmer might declare variables but forgot to initialize before use. And this can lead to undefined behavior or non-deterministic bugs. They are difficult to debug. Or most importantly, they can lead to security issues. For example, if a previously deallocated sensitive data is leaked. And according to survey is done by Herb Sutter, that is use of before initialized condition is the fourth large class of the memory safety vulnerabilities. And the current CHERI design is supporting spatial safety and temporal safety as a default. Our goal is that how we can extend this CHERI hardware to provide initialization safety also. Uh, Let me step back and explain what is CHERI. CHERI is a IC extensions which replace the conventional pointer with capabilities that enable fine-grained memory protections. For example, if you have some 64 address space, it doubles the width, and you can have permissions bits or you can have bound, such as for here you can have a pointer, and after that you can say that this pointer can reach you can reach this area, but not this area, or you can have some permissions, for example, readable and writable memory area. However, the problem is with that the CHERI capability are static; they don't change dynamically. If I want to detect initialized memory access, I need more dynamic solutions. Dynamic solutions means that, for example, if a memory area is do some store, I will allow them to read it. To solve this problem, we introduce conditional permissions. These conditional permissions are the permissions forms of X before Y. It means that if a permission Y is granted, if operation X occurs. On architectural levels, operation on a memory are limited to load, store, or execute. Permissions can be limited to read, write, or execute. For example, if I want to implement write before read, I want to say that you can get read permissions dynamically, at least one store operations occurs using that capability. This is a general concept of our idea, but you can define, I just explained right before read, but you can apply these conditional permissions for different use cases. A notable example can be right before execute, especially for if you have some JIT compiler. This is important. You can say that memory must be written at least once before execute access is granted. I will explain the whole idea with describing the different challenges. For example, if you have just a single variables, you can just detect this. You can just detect. You just need a one bit to say that okay, this memory this variable is initialized. But how you will track of that conditional permissions for larger memory area? If we have a such as arrays or larger object, we need to track that which part of the memory region has been initialized. That's why I need a way to track that where the store happens. To solve this problem, we introduce operational bound. Operations bound work like that. At allocations time, I am just saying that, okay, when this capability lifetime is start, I want to give a permissions that it is just writable memory area. But when a store occurs on that area, I want to increase the operation bound to say that, okay, this memory area is now writable and readable memory area. And if a adjacent store happens to that area, I will increase the operation bound. At the end, actually, when we reach the operation bound to upper bound, it will be the normal capability as it before, as it before. Yeah, this is the general idea, and as you realize it, that how I will keep track of this additional bound, because I already say that this CHERI capability itself is really compact, because you have 64-bit address, and after that you have hardware permissions, user permissions, and I need to encode this extra operation bound to track that which memory is initialized. I need to encode this operation bound. What I did that is I encode this operation bound in the address space on the last 16 bits. It is just it is a lot of mathematical calculation how I encode it. I will not go into details, but if you are interested in, please go in and check our paper. The second challenge is that, assuming that you have a let me explain this way. With operation bound, actually, we essentially introduce some state to the conditional capability. But what happens if you have a multiple capabilities point to the same memory area? And this cause problems that consistency of operation bound across the different capability. To ensure that this consistency, we introduce something we called store linearizations passed to the LLVM compiler. And this pass is linearized memory access in LLVM IR, and by doing that ensures that all capability referencing on the same region stay sync in terms of the operation bound. And I will explain now high-level architecture. From compiler side, what I did that I implemented right before read compiler options or function level annotations or variable level annotations. And after that, on the LLVM IR side, we have a conditional permission instrumentations that whoever has these annotations, I instrument with right before read permissions. I already explained the store organizations pass that to ensure consistency between during the lifetime of this capability. From the hardware side, what we implement is that I already said that I introduce, I of course, just let me recap that I introduce now operational bound and I encode that one into the capability. And I have a new instructions to set this operation bound. And most importantly, that what I changed that whenever a store happens, I need to update the capability that show that this memory is initialized, and to detect initialized memory access. Whenever load happens, I check that this operation is between operation bound and upper bound. And there are more details. Please check the paper. For evaluation test cases, we evaluate this Moncherry with Juliet test suite on the QEMU full system emulators, and we mostly focusing on use of uninitialized variables. This consists of 560 good and 560 bad cases. Moncherry able to detect all the test cases, but some cases we realize that we have some false positives. This false positives case exhibits uninitialized behavior, but such behavior is benign from a security point of view. For generally, I am getting a lot of question about this false positive test cases. That's why I will show one example cases later after introducing performance and area cost. We implemented Moncherry in CHERI-RISCV FPGA flute core, and we have two percentages overhead. From the performance perspective, we have 3.5 when we run on CoreMark. This is actually from not the hardware changes what we did, that I introduced the store organization pass, that the store organization pass is changing a lot, changing a lot how the program it is. That's why we got this overhead. And let me step back and explain why Moncherry introduced false positive cases. And this is one of the example from the Juliet test suite. And I have some good example here. Good means that there is no initialized memory access, but Moncherry is able to detect. And I am sending some data to the another functions, and to another function is copying pointer to the another one. And after that it is loading into the another variables. As you see that it is a bit artificial examples. Normally you don't expect that developer do this kind of coding. uh, from the actually, if you think about it, Moncherry cases, that is data when we this tree is here. From Moncherry perspective, it is still initialized memory access, because still operation bound is 0 for this data, but we are loading onto the another data. You can think about that from architecture level, this is really initialized memory access. But if you think about the whole program, in the for, developer is already declare a variable here, right? And you can think about it that from programmer perspective, it might be benign. From architecture level, this is initialized memory access. For all 6 cases, we have this similar pattern. And as a result, just if I want to recap this, we introduced conditional permissions and conditional capability to CHERI architecture, and we have full QEMU full system emulator, and we implemented also on the hardware, and we have full compiler support, and we evaluated our system with Juliet test suite and CoreMark. Yeah, thanks for listening.